Yeah, let's continue mass spectrometry. So far, we learned the isotope effect. You see, in the uh, mass spectrometric pattern, okay, the isotopes are all detected, separately detected. So by examining the abundance of the um, the isotope, and then we can infer the what kind of elements are there, and even we can infer the structure of the compound. Okay, here we already learned that um, see this example, all right, and from the mass spectrum, yeah, and from the spectrum pattern, you can know the the number of carbon atoms, okay, and even we can know what kind of elements are there. Okay? Let's look at this figure, yeah, figure 7. These histograms indicates that calculated isotopic patterns for series containing uh, chlorine and bromine. You see, chlorine and bromine are exemplary elements that have, you know, the isotope whose masses are very close. Okay, for example, uh, the chlorine. Yeah? Chlorine, the most abundant um, chlorine in isotope is the mass number 35, and there are also relatively um, high abundance of other isotope whose mass is 37. So the ratio is 10 to 32. Okay. What more dramatic one is bromine. Okay. Bromine has a main two main isotopes. Okay. Uh, the one is, let me see. I'll show you this one again here. Bromine mass number 79 and mass number 81. Their abundance is almost identical. Okay, mass number 79 is a little bit has a little bit higher abundance, yeah, 50.69%. But mass number 81 also uh, is almost half, yeah, just a little bit smaller than the mass number 79. Yeah? This abundance is 49.31. Okay, this mass distribution gives us a very good insight um, into the compound, whether the compound contains bromine or not. Okay, let's look at this mass spectrum, right? And let's concentrate on this one, these two, peaks. Okay, and the peak at mass to charge ratio 130, 136 and 138. Okay, this one. This is at the these two peaks are almost identical. Okay, or this one too. Okay, and but this one is a little bit larger than this one. Mass number 136 is the main peak here, but this one mass number 138 is also, the this relative abundance is almost identical, same as this one. So we can conclude, oh, this one contains bromine. Okay, and also this one is as same. This is molecular peak, and this one 107, and this one the next one is 109. Okay, but their abundance is almost identical, so we can conclude, okay, these two fragments, oh, I'm sorry, this is not a fragment, this is a molecular peak. Okay, this fragment contains one a bromine, uh, the atom in the molecule. Okay, okay, let's look at this figure again. Okay, when there is only one chlorine, okay, and chlorine has two main isotopes, okay, whose abundance is 100 to 32, okay, we can expect this relative abundance. But what about the uh, chlorine 2, dichlorine, okay, Cl2, and of course, yeah, the X is the main peak, okay, this is base peak, and since the mass number is different by 2, so we can expect there will be, two peaks at x plus 2 and x plus 4. Now here, okay, you see the this is the mass distribution, and I strongly recommend you calculate this relative abundance, okay, as this one, x as a base peak, okay. This is good example, all right. Yeah. And you can do it very easily, okay. You can use uh, this table, okay. And for chlorine 3, the Cl3, and then we can expect that there are 4 peaks here, okay. 1, 2, 3, 4 peaks at x and x plus 2, x plus 4, x plus 6, okay. Let's now look at the bromine, okay. For the bromine, we expect two nearly identical peaks at x and at x plus 2. And what about the Br2? Okay, this is quite peculiar. Okay? The base peak is not x but x plus 2. Why? No, you have to think about that, no? Right? And Br3, and there are 4 peaks, okay? Because there are 2 um, almost equally abundant isotopes, okay. So Pr3 has 4, 1, 2, 3, 4 isotope peaks like Cl3, okay. And this one Pr2 Cl, okay. And then you expect 1, 2, 3, 4, okay, isotope peaks, but the main peak, base peak is at mass number x plus 2, and Cl2Br. We expect that this kind of mass spectrum. It is very interesting and very see, good for you to calculate this mass relative mass abundance for each species. Okay, I strongly recommend you to do that. Okay. Okay, now let's consider high resolution mass spectrometry. Okay? But here, up to this point, we simply consider this well separated, well defined mass whose mass numbers are integer. Okay, 136, and this is 138. Okay, this one is 57, and next one this must be 58. Okay, like that. There is no decimal points. Okay, because since we only consider up to this point, we only considered what, the nominal mass. Nominal mass means the mass numbers are all integer. Okay, but let's consider these two compounds here. Okay, C5H8O plus ion and C6H12 plus ion. Their nominal mass is identical, 84. Okay, this one is also 84. All right, but how do we determine, how do you distinguish these two ions by mass spectrometry? Our knowledge so far, with our knowledge, we cannot do it, but it is possible with high resolution mass spectrometry. High resolution means that this mass spectrometer can distinguish very small mass difference. How small? Let's look at the exact mass for these two compounds. Okay? This one, exact mass is 84.05696. Okay, but this one, the mass number 84.09335. Okay, so there is a difference in the second decimal point. Okay, very small difference, but with high resolution mass spectrometer it is possible to distinguish, okay, these small difference. How? With a double focusing mass spectrometer, a time of flight mass spectrometer, an Orbitrap mass spectrometer, or a Fourier transform ion synchrotron resonance mass spectrometer is possible. Now we can resolve the difference of 0.001 or uh, less at mass number 100. Okay, yeah. Here is an example, and let's consider these two species again. Here, yeah, we can calculate their exact mass. Yeah, from 5 carbon atoms. Carbon atoms. By definition, yeah, its mass is 12.0000. Okay, and from 8 hydrogen, yeah, we here the mass is 0.007825, like that. From oxygen mass is 15.099, yeah, like that. Okay, and since this one lost one electron, here we have to consider electron mass. But in usual case, electrons are so light compared to the nucleus, so we simply ignore the electron mass. But here, yeah, now we are calculating the exact mass. So let's consider this electron. One electron is lost, so we take we minus, okay, one electron mass, okay, which is 0.00055. Whoa, it contributes here. Okay, so exact mass is 84 point, yeah, here 05696. But observed mass is 84.0591. All right, yeah. Yeah, here maybe we can ignore the electron anyway. This is the exact calculation. But and then let's do the same calculation for this compound. Okay, and then we get 84.09335. Okay, and observed mass is what? Wow, it's very exact. Okay, 84.0939. Okay, and look at this one. This is a different one. Okay, and this spectrum was obtained with high resolution mass spectrometer. Okay, and nominal mass is 031. Okay, look at that. Hmm? This x-axis, 31 is here. Okay, and this one, the left hand as a spectrum, is 30.97. It's almost identical to 31. The mass difference is only 0.03. Yeah, but in ordinary mass spectrometry, and these three peaks are not distinguishable. Okay, in this one, and this one, this very peculiar, the ion, mass distribution is like that. Okay, but this one is here. But important is that with high resolution mass spectrometer, all these three species are distinguishable, although their nominal masses are the same. Okay, that's the point. Okay, the next topic is rings plus double bonds. Okay. Sometimes we don't know the structure of the molecule of our interest, and if we know the composition of a molecular ion, okay, here is the composition, and then we can calculate the number of rings and double bonds, okay, the sum of these two, and we want to propose its structure, a handy equation that gives the number of rings and plus double bonds, yeah, R plus dB. The equation is this one, yeah, R plus dB equals C minus half of H n plus half N plus 1. Okay. Here C is the number of group 14 atoms. You know, group 14 is a carbon family. Carbon, silicon, and what? Next one is germanium and what? Uh, antimony and the lead. Okay. You know, they have some commonalities. Okay, which is they all make 4 bonds. Okay, and H here is the number of uh, hydrogen and halogen atoms. They make only one bond. Okay? And N here is the number of group 15 atoms: nitrogen, phosphorus, arsenic, and what's the next one? Antimony and bismuth. Okay, and so on, which make 3 bonds. Okay, and group 16 atoms. This is oxygen family: oxygen, sulfur, and what? Selenium, polonium, tellurium, and polonium. Okay, which makes 2 bonds. Do not enter the formula here. You know that doesn't apply for the group 16 atoms. All right. And here is an example. Yeah? This is a quite complicated molecule, and let's apply this rule, this formula, rings plus double bond formula. Okay, here, how many rings? One ring here. Okay, how many double bonds? 1, 2, 3, and 4. And let me see. Uh, is that all? Uh, no, there's one ring and double ones 1, 2, 3, 4, and total is 5. Okay, let's see. Let's apply this formula to see if we can get number 5. Okay, and C. Let's count. C is number of group 14 atoms here. How many carbon atoms here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and here 11, and there are 4 carbon atoms here. Okay, and then total is what? 6 plus 4, 10, and here 3, 13, and 14. Here 14, and another one, silicon. Silicon is also a member of group, you know, the carbon family. Okay, here, so plus 1, and minus. Let's calculate, count the H. H is hydrogen and halogen. Okay, how many hydrogen atoms here? 1, 2, 3, and here 6. 1, 2, 3 plus 6. It's a 9, and here it's a 9. Okay, let me see why it is not easy. Here is 6, and this one is 9, 15. Here there are 2, 17, 18, 19, and 20, and more. Let me see. It must be 22. Okay. Here is nothing. Only 1. Yeah. And here 6, 7, and 7 plus. Let's see. 9. The 15. Here 15, and 2, 17, 18, 19. I'm not sure. But this is the what the chemical. You see, here is a 22. Let's calculate, count again. Okay, let's do this one. 6 here, and 9, 15, and 2 here, 15, 17, 18, 19, 20. Where are 2? The 2 hydrogen atoms. Anyway, and plus 1 is what? In halogen. There are how many halogen? Bromine and chlorine. 1 and 1. Okay. not sure, where I lost. Uh, Anyway, okay. Oh yeah, we cannot hesitate here, and let's see what is n. N is the number of group, 15. Okay, what is the nitrogen and one nitrogen? Okay, and what an arsenic here. Okay, and plus one. Huh? This is default value, and then this calculation gives you a 5. Okay, and yeah, let's finally let's count hydrogen atoms. How many are there? One, two, three, and no more here. One, two, three, and four, five, and here five plus, and let me see, the nine. Okay, 14, and here, let's see, 14 plus 6. That's 20. Yeah. Well, uh, I'm not. I'm sorry. Yeah, you do that. Okay, you do that. Anyway, this formula is convenient to calculate the number of rings plus the double bonds. Yeah? This information is good to infer this structure. Okay, identifying the molecular ion peak here usually this one, the peak at highest mass to charge. Yeah? It is there is a high chance that this peak corresponds to a molecular ion peak. Okay? But here, let's say these two species, their structure is, although they have the same number of each atom, but the structure is different. So the fragmentation pattern is also different. Okay, but the question is, how would we know that peak at MZ100 here? Okay, but this one is a small peak next to this big one is the molecular peak plus one. Okay, this 100 represents the molecular ion. Okay, yeah, that's the question. Yeah, here are some guidelines for identifying the molecular ion peak. This one, molecular ion peak, will be at the highest mass number, okay, mass to charge value of any of the significant peaks in the spectrum that cannot be attributed to isotopes or background. That means that this one, uh, that means we ignore this one, small one. This is quite small relative to the, the very next peak, right? Because this is due to the isotope, okay? And background arises from sources such as pump oil in the spectrometer and the stationary phase from a gas chromatography column. Experience is required to recognize these signals. Okay, background also contributes the message to the message spectrum. So you have to be well trained to distinguish. Okay, oh, this is from the background or not. Okay, so experience is required, right? With electron ionization, the molecular ion peak intensity is often no greater than 5 to 20% of base peak, okay, and might not represent more than 1% of all ions. All right. So when you use electron ionization, okay, here this is from electron ionization, and this is the base peak. This is now set at 100, and this is this peak abundance, relative abundance is between 5 to 20%. Okay, but if this one peak at 100 is very high, and then may not be a molecular peak. Okay, and intensities of isotope peak at M1, M2, and so on must be consistent with the proposed formula. Okay, so we learned already how to consider the isotope. And third, the peak for the heaviest fragment ion should not correspond to an improbable mass loss from. It is rare to find a mass loss uh, in the range 3 to 14 or 21 to 25. Okay, mass loss is always there. Okay, especially when we employ electron ionization. Okay, but mass loss, common mass loss include this one 15, because metal group may be removed from the structure, so its mass is 15. Okay, or 17, yeah, OH hydroxyl group or ammonia may be lost from the structure, yeah, and this mass contribution is 17. Not in this region, 3 to 14 or 20 to 25. And 18, mass loss of 18 may occur because H2O, this one will be lost. Or 29, which is from C2H5, and 31 from this methox group. And 43, this is what's the name for this one? This is the propyl group, and this is acetyl group, yeah, and many others. Okay? If you think that the mass to charge ratio 150 represents, but there is a significant peaks at 150 45, then is not assigned correctly. Okay, you understand? Because there is a mass difference is only 5, and then this 5 is 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 uh, is very improbable, right? Because mass loss in the range of 3 to 14, this is very rare case. Okay, that means what? Since there is only 5 mass difference, so this mass number, mass 150, cannot be molecular ion peak. Okay, yeah, mass loss 5 dalton is improbable. Alternately, the two peaks represent ions from different compounds, or both peaks represent fragments from compound whose mass is greater than 150. Okay, this means that you observed these two, peaks, relatively strong peaks, and then they are not uh, molecular ion peaks, so you can think that molecular ion peaks are not appeared, but uh, the molecular ion has higher mass number than these two numbers. Okay, if a fragment ion is known to contain, say, three atoms of element X, then there must be at least three atoms of X in the molecular ion. Okay, the, element X, let's say, yeah, uh, three atoms here, and then there must be at least three atoms of X in the molecular ion. Okay, because fragment ion contains three X elements, so molecular ion must at least contain three or four, five. We don't know yet, but at least three X atoms. Okay, X elements. Okay, let's revisit this method, this method spectra. Okay, for this 2-hexanone and for methyl 2-pentanone. Okay. This one, uh, mass number 100 is molecular ion peak, yeah? And this one, mass number 101, yeah, m plus 1. This only takes 6%. Okay, let's calculate the number of carbon atoms. Okay? Number of carbon atoms is observed. Okay, uh, the ratio intensity of these two. Okay, why? Because this one mass, this mass is 101. Okay, only one mass, greater. Okay, and then we can rationally think that this one mass number one difference is due to carbon 13, not carbon 12. Okay, and we calculate first the this one intensity ratio of these two peaks, and then divide by contribution per carbon atom. Okay, you see, uh, which is 1.08%. Okay, you see the relative abundance of carbon 13 is 1.08% only. Okay, when we set the carbon 12 as 100. Okay, and it gives uh, 5.6. Okay, this is close to 6. So we can say, aha, this compound contains 6 carbon atoms. Okay, okay, let's look at this one. 1, 2, 3, 4, 5, 6. Okay, there are 6 carbon atoms. Okay, the same same calculation is applied to this spectrum. Okay, and then we also find that there are 6 carbon atoms. Okay, here 1, 2, 3, 4, 5, 6. All right. So if there are 6 carbon atoms and no nitrogen atoms, a possible composition is, okay, yeah, assuming that with nitrogen atoms, the mass molecular ion pair, the mass number is not even number, other number. Okay, so we simply ignore there is no nitrogen atoms. Okay, and then possible composition maybe this one. Okay. Oh, you may ask, oh, professor, is this the only one that gives mass number, molecular the mass number 100? Maybe not, maybe not, but we have all kind of possibilities, and this is a very strong candidate. Okay, 6 carbons and 12 hydrogen atoms and 1 oxygen atom. Okay, the expected intensity n plus 1 here. Yeah, we apply again. You know the we previously we did let's see let me see, yeah, this kind of calculation. Okay, considering the isotope, but in this case here we consider all the isotope effect from not only from carbon, although we consider only carbon isotope effect, but now here we consider all the isotope effects from the deuterium and the oxygen 17, but their contributions are small compared to carbons, right? Here, since that's why we only consider the contribution of carbon, because its isotope effect, contribution is 1.08%, but hydrogen and oxygen, their contributions are quite small. And then, anyway, the calculated intensity of this one is 6.7%. All right? Yeah. So it makes sense here. The observed intensity of 6% for n plus 1 is within experimental error of 6.7%. Okay, this observed one here. If we blow up this part, and then you'll find, oh, this height is about 6%, but our calculation is 6.7%. Yeah, within experimental error, they can be considered as identical. Okay, yeah, okay, and this one requires one ring or double bond. Okay, yeah. And actually, the this is a structure. There is no ring, but only one no, one double bond. Okay, so if you want, you can apply. Let's see, this formula, yeah, to to calculate the ring plus double bond. Okay, and then you will find that formula gives you only one. Yeah. Okay, here is the one double bond here. Okay, not ring in this case. Okay.